r squared times the altitude h, which would be a third. Pi, you could choose pi, so we use 3.142 as pi. We'll use r squared as half of the diameter. Now the diameter, half of the diameter squared. Now, so to get r, we'd say if the diameter is always equal to 2 times the radius, because you'd have one radius here and one radius here. So if the diameter is 70, to get one of the radii, we'd have to take the diameter and divide it by 2 to get what that radius is. So 70, which is the diameter, divided by 2 would give us the radius, which would be 35 millimeters. So h here would be 35 millimeters. So pi was 3.142. R is 35 millimeters, but we have to square it, so we put our squared sign, and then h will be altitude. So our altitude will be 100 millimeters. So that calculation will give us our volume. Okay, so we just have to put that into the calculator, and the answer we would get would be in millimeter cube, because the volume unit is always equal to the length unit cube. Okay, so when you do this calculation, you should get 128,298 millimeter cube to the nearest millimeter cube when you do that rounding off. Okay, so that would be number 6. Okay, so in exercise 107, number 12, we say that this shape here represents a bird cage in the form of a cylinder surmounted by a cone. The diameter of the cylinder is 35 millimeters and the height is 25 millimeters. The total volume of the bird cage is 31,178 cm cube. That is the total volume, right, of that bird cage. Calculate A, the total height of the bird cage. So the first thing we'd have to do is to find the total height of the bird cage. Total height. Okay, so if we have to find the total height of the bird cage, it means we have to get the height of the cone portion. Right, we have to get that portion there. So we could call that H1. And then we have to add that now to the height of the cylinder. That will give us our total height. Good? Now what do we have? We have the volume. So we need to find an equation that connects the volume, which is the total volume here of the bird cage, with the missing height, and then we solve for that. Okay? So the total volume V of this bird cage will be equal to the volume of the cone plus the volume of the cylinder. Now the volume of the cone, we know, will be a third multiplied by the area of the base multiplied by the height. And the volume of the cylinder will be the area, the cross-sectional area of the circle, right, of this circle here, of the cylinder, times the perpendicular height. Okay, so that's how you would find the total volume. You have to find the volume of the cone first, which is this, volume of the cone, and we'd have to add that to the volume of the cylinder. Okay, so let's see what happens now. The volume of the cone will be a third times the area of the cone. area of the base of the cone, which will be this area here. And that will be the same area as this cross section of the cylinder. It's the same circle. So we could actually do a little mathematics here first, if we would like to, and make our calculation a little easier in the end by taking out A as a factor, seeing that these two areas is the same. You notice that this area here and this area here is the same. So you could actually take out A as a factor and leave H as the unknown in that equation. So we could do something like a third into, let's write it back just to have it a little closer, like this. And if we say V is equal to this, we could say that V is equal to A into a third H plus H here. Now this H here is the height of the cone, which would be H1 really, right? That's the height of the cone. And this H here is the height of the cylinder. Let's put that there. Okay, so we wouldn't get confused. So now let's see what we have. V is equal to the area A here, which is the same thing as A here. A squared. Why would it be A squared? No, remember, we're breaking it up into two solids, right? So, well, A squared means A multiplied by A. We're not multiplying, we're adding, right? So that's why it wouldn't be that. So this here really is A into a third H1, which is this height here, plus the height, which is 25. Okay, so I was just seeing if I could simplify it in a way that would make it work out easier, because our task really is to get what this here is, this H1 is. Right? Because they asked us, find the total height. We need to get what H1 is. So to get the total height, we'll add H1 to 25. Okay, so that's really our task. So I'm using the equation to see if I could put it in a way that we could easily find this without having to do too much calculation. Okay, and so let's see what would happen here. So I could put in the figures now, or I could still work with these symbols and see what happens. So now if I divide both sides by A, I'll get V over A, dividing this side by A and this side by A, will be equal to a third H1 plus 25, right? I divide both sides by A. The next thing I could do is say minus 25 on the right hand side, minus 25 on the left hand side. So what happens is that this becomes V over A minus 25 equal to a third H1, right, so far. And the last thing I'll do is to remove the third, right. Now a third is the same thing as dividing H1 by 3. A third means divide H1 by 3. So the reverse of dividing H1 by 3 is multiplying it by 3. So I'll do multiply by 3 on this side will give me H1, and therefore I'll have to multiply by 3 on this side as well. But multiplying by 3 on this side means this. This 3 has to be multiplied by V over A minus 25. Okay? So now we have an expression or equation for H1, which is our height. Right? Again, we have to get this and then add it to that to answer the first question, is find the total height. So let's put in our figures now. This will be equal to 3 multiplied by V is the volume, which is 31178. 31178 divided by the area. Now the area is pi r squared. The area is pi r squared. That's the area of the circle, which would be 3.142 multiplied by the radius squared. What is the radius of this? the radius of this will be 35 divided by 2. 35 divided by 2 is 17.5. So that'll be pi r squared, because this is the diameter, right? That's the diameter. We don't want the diameter, we want the radius in this equation. So we have to divide 35 by 2 to get the radius, and then you square it. Okay? So if you work out 3.142 by 17.5 squared, you get 962.2375. .2375, and that will be the area in centimeters squared. Okay, so that's the area. So the area which we have in this equation here is that figure there. So we put it in 962.2375. Okay, so that will be V over A minus 25. Minus 25. Okay, so I'm hoping that works out. Let's see what happens. Okay, you get 32.40. So this works down here to be 3 into 32.40 if you round this off. All right, minus 25. And then this will work out now to be 7.4 in the brackets, multiply by 3, you get 22.2. So this will be 22.2 centimeters. So this H1 on top here, right, this H1 is really equal to 22.2 centimeters. Okay. Now there may be another way to treat with this point here, but this is just the way that I treated with it to get H1 as the subject of the formula, right? To make H1, this is what we needed to find out. But still, even though we went through this procedure, we still haven't answered A, which is to find the total height. Because all we have now is the height of the cone. Right? In order to get the total height now, we'd have to add the height of the cone to the height of the cylinder, which is 25 centimeters. So therefore, the answer in this case here, to get the height of the cylinder, of the total bird cage, which is made up of the height of the cone and the height of the cylinder, we'd have to add the two together. So that will be equal to 22.2 plus 25. And that answer will be in centimeters. So that final answer there will be 47.2 centimeters. Right? That will be the answer for part A. In part B of number 12, they said, calculate the surface area of the cover for the cage, except for the base. Except for the base. So we look at this here, and if we were to cover the entire cage, which these two shapes represent here, you would have to find the surface area of the cone, and you'd have to find the surface area of the cylinder. Now the surface area, therefore, of the cover would be equal to the surface area of the cone plus the surface area of the cylinder. Now the surface area of the cone is pi RL, and the surface area of the cylinder will be 2 pi RL, right? Where in the case of the cone, the L is the slant height, and in the case of the cylinder, the L would be the perpendicular height. Okay, so let's see what happens here. Now, in the diagram, they did not give us the slant height of the cone, right, which makes it even more interesting. They didn't give us the slant height here as part of our information, right, which we need to get the surface area of that cone. Okay, so we would have to use some technique to be able to generate that slant height, to be able to get the surface area. So the technique we will use is that we will drop a perpendicular line down to the base here of the cone, come across with another perpendicular line like this, and recognize that we will actually have two sides of a right angle triangle. Okay? The two sides we will have will be this vertical side, which will be 22.2. So this side here will be 22.2 centimeters. And the other side here will be equivalent to a radius. So if this is 35, the radius, as we had discovered previously, would be half of 35, which worked out to be 17.5. So it means therefore that this dimension here will also be 17.5 centimeters. Okay? This dimension right here. So we will have to use Pythagoras' theorem to generate what L would be, right? Because it's a right angle triangle. So by Pythagoras' theorem, the hypotenuse in this triangle here, let's call this triangle A, B, C, right? The hypotenuse L, which is the same as AB squared, is equal to side 1 squared, which is AC squared. So that will be 17.5 squared, plus side 2 squared, which would be this side here, which would be BC. That would be 22.2 squared. Pythagoras said that in any right angle triangle, the hypotenuse squared is equal to the sum of the squares of each of the other two sides. Okay? So from there now, we could work out what L is by taking the square root on both sides. If you take the square root of anything squared, you get back that original thing. And if we add these two, we'd have to take the square root of that to work out what L is, because we have to take square root on both sides. So we'd have to work out what 17.5 squared is plus 22.2 squared. Find the square root, and that would give us L. So you can work that out now on the calculator and see what you get. Okay, you should get 28.27 as L. And that would be 28.27 centimeters. Now, we would use this now. What we should actually do is round it off to the nearest, to one decimal place, because that's what we were working with all the way through. So let's round this off to 28.3 centimeters. So we'll use that rounding off position all the way through. So having gotten that now, we could work out an equation now for S by saying S will be equal to pi, which is 3.142, R, which is the radius here of the cone, which would be 17.5, L, which we just worked out to be 28.3, right? That will give you your surface area of the cone. And now we'll have to get the surface area of the cylinder, which would be 2 by 3.142, that's pi. R will be 17.5 again. And L in this case is the vertical height, right, which would be in this case 25 centimeters. Okay? And that will give you the total surface area of the cover that would have to go over those surfaces. So the task now is to work out that and see what answer you get. So you can try it and see. Okay, so your final answer for the total surface area of the cover, which would have to cover those two shapes, would be 4,305.3 centimeters squared. Okay? Okay, so that triangle didn't come out initially, so if you have a look at it now, you'll see that ABC is the triangle that we use in the calculation. Okay, and last question we look at is number 21, which says that a pyramid has a rectangular base 8 centimeters long and 5 centimeters wide. Right, so if you have a rectangular base and it says 8 centimeters long, 5 centimeters wide. So this here will be 8 centimeters, this will be 5. It also has an altitude of 7 centimeters. Right, so it means that the height, perpendicular height here, will be 7 centimeters. Okay, like that. So that's what the pyramid would look like. And they're basically asking you to find the volume of the pyramid. And that would be easy because the volume of any pyramid is a third times the area of the base times the altitude h. In this case, the area of that base is the area of a rectangle, which is length by breadth, in this case, or length by width, which in this case will be 8 by 5. And then the altitude is 7. So, very simple question, straightforward. So you just work that out. Okay, so multiply it and see what you get. Okay, so your volume would be most accurately put at 93 1/3 cm cube. If you're rounding it off, it will be 93.3 cm cube to 1 decimal place. Okay, so that would be the answer for number 21 in this exercise here. Okay, so we're continuing with the theorems for the angle properties in a circle. And this theorem that we're looking at, which is theorem 4, Theorem 4 says that the opposite angles of a cyclic quadrilateral are supplementary, which means that if we have a cyclic quadrilateral, which is a quadrilateral having its 4 vertices lying on the circumference of a circle, as shown in this diagram here, right? These vertices lie on the circumference of the circle. Then that is a cyclic quadrilateral, and it means that the opposite angles in that cyclic quadrilateral are supplementary, which means they add up to 180 degrees. So that is theorem 4, right? So you could write that opposite angles in cyclic quad, short for quadrilateral, are supplementary, or you could put sum to 180 degrees. Okay, so you shorten it up accordingly because you'll have to be stating that in the exam, right? When you're using the theorem. So in my diagram, the angle at Q plus the angle at S, when you add them up, they'll be 180. The angle at P plus the angle at R will be 180. Okay, so that is what they're talking about here. Now, we will do an example, and you're writing down now the example that we'll be solving to deal with this theorem. So write in example. Without measuring find the value of the unknown angles. Find the value of the unknown angles in the circle. Giving reasons for your answers. That is, without measuring, find the value of the unknown angles in the circle, giving reasons for your answers. Okay, so you take down the diagram there, and we are putting in what they gave you. They gave you the angle at P as 43 degrees, and they give you the angle at Q as 98 degrees. So therefore, we would have to solve for the unknown angles, which would be the angles at R and the angles at S, which we are calling X here and Y here. Okay, so this is what you have to solve for. Okay, so in order to answer this question, which is really to find the values of X and the values of Y, and the value of Y, we have to recognize, first of all, that PQRS is a cyclic quadrilateral. And that implies, therefore, that the opposite angles are supplementary, which means that they sum up to 180 degrees. So in this cyclic quadrilateral, the angle at P and the angle at R, first of all, are opposite, right? And therefore, they are supplementary, which means they add up to 180. So we could write angle X plus 43 degrees, right, must add up. When you add up, they must get 180 degrees. And the reason is that opposite angles are supplementary in a cyclic quad. So you must put that in, right, in whatever shortened fashion that you need. So you say opposite angles are supplementary. Okay, shortened format. So if that is the case, it implies therefore that angle X will be equal to 180 degrees minus 43 degrees. Which means that angle X will be equal to 180 minus 43, which will give you 137 degrees. Okay, so we would have solved there for angle X. In a similar fashion, you could solve for angle Y. We could also write that angle Y plus 98 degrees, which would be angle Q, must also work out to be 180 degrees. And it's because of the same reason, seeing that it's a cyclic quadrilateral we're dealing with, we know that opposite angles are supplementary. Meaning that those angles, when you add them together, you get 180 degrees. So you give them the reason when you make the statement, and it means now you could solve for angle Y by saying angle Y is 180 degrees minus 98 degrees. So angle Y is 180 minus 98, which works out to be 82 degrees. So in that way, we would have solved for both angle X, so you write answer here to ensure that they know that that is an answer. And we would have solved for angle Y as well, and we write answer there as well. So they know exactly what is what, okay? You're very clear in what you're giving them. Okay, so we're on to theorem 5. Theorem 5 says that the exterior angle of a cyclic quadrilateral is equal to the interior opposite angle. So the exterior angle of a cyclic quadrilateral is equal to the interior opposite angle. Okay? So for a cyclic quadrilateral, the exterior angle is equal to the interior opposite angle. Alright? So if we look at this diagram here, you'll see that first of all, that the shape A, B, C, D is a cyclic quadrilateral because the vertices lie on the circumference of the circle. And each of the angles at the respective vertices A, B, C, and D are labeled accordingly, right? So what they're saying is that, let's see, the exterior angle equal to the interior opposite angle. What are we referring to? So let's take up this one. Let's say, for example, the exterior angle here will be this. Right? That exterior angle here will be equal to the interior angle opposite. So the exterior angle is equal to the interior opposite. That's B. So it means that this exterior angle is equal to B. The exterior angle is equal to the interior opposite. So down here I need to write angle B. That will be angle B there. Right? This angle here is angle B. If we do another one, let's say we look on this side here. Let's see what else we look at. Let's look at another one here. Okay, so on this side here, the exterior angle here will be this. Right? The exterior angle here is equal to the interior opposite. So the exterior angle here will be angle C. Because the exterior is equal to the interior to this, which is one on the inside of the shape opposite. So these two will be equal. Okay? So that's the procedure that we will use to determine the various angles. Right? And in the question that is to follow, we will be using that particular relationship to be able to solve it. And the diagram that we'll be referring to is this diagram here, which you'll have to take down, but take down the question in the meantime. Okay, so the question is, without measuring, find the magnitude, find the magnitude of the unknown angles in the circle. Without measuring, find the magnitude of the unknown angles in the circle, comma, stating reasons for your answers. Stating reasons for your answers. Okay, so what we have to recognize here is that we will be using this property here. So if we use the property that the exterior angle is equal to the interior opposite angle for a cyclic quad, we could say that if we look at 85, right, if we look at 85 as the exterior angle, it must be equal to the interior opposite. That is to say, angle Q must be equal to 85 as well, because it is the interior opposite relative to 85. So we write that angle Q must be equal to 85 degrees, and the reason is that the exterior angle is equal to the interior opposite angle. Okay, so this is what we wrote down. So therefore you would have solved for angle Q already. The next thing that you'll write is that angle Q plus angle S must be equal to 180 degrees because they are opposite angles in a cyclic quadrilateral. We just learned that theorem, right? And we know that opposite angles in a cyclic quadrilateral are supplementary. That is, they add up to 180 degrees. So we say angle Q plus angle S must be equal to 180 degrees. And you put the reason next to it right here. Opposite angles are supplementary. Right? And we know they're supplementary because they're in a cyclic quadrilateral. Therefore, seeing that we know that angle Q was 85 degrees, so 85 degrees plus S, angle S, must be equal to 180 degrees. Okay? So, in that case, it would mean that angle S will be equal to 180 degrees minus 85 degrees, minus 85 on both sides, and we'll get that angle S must be equal, therefore, to 95 degrees. So in that way, we would have solved for both the missing angles. Angle Q, so you put answer next to that because you know that's one answer, and angle S, that will be another answer. Okay? So we apply theorem 5, and actually that was theorem 5, and we apply theorem 4 to solve this problem. Right? The current one and the one before it. Okay, so we're looking at theorem 6 now. Alright, we are on to theorem 6. And theorem 6 says that the radius of a circle drawn to the point of contact of a tangent is perpendicular to the tangent. So, if we observe this diagram here, OT is the radius drawn from the center of the circle to the point of contact with the tangent AB. And what it says is that the angle between that line, right, O to this point here, T, right, and the tangent at that point of contact or point of tangency, that angle there will be 90 degrees, right? It will be 90 degrees at that point. So that is something that we have to be aware of, and therefore we'll be looking now at the question that will help to solve, to help us to understand that a little better. Now, you would see that in this diagram, the information they gave us is that TA is a tangent to the circle, and ONT is a straight line. ONT is a straight line. Given that OTA is equal to 24 degrees, OTA is equal to 24 degrees, calculate, they want us to find, first angle is angle OAN, that's the first angle, and then the second angle is angle ONA. Okay, so those are the two angles. So first of all, we have to understand what each angle is. Where is angle OAN and where is angle ONA? Now, if you observe on this diagram, they haven't drawn all the lines to be able to give you OAN nor ONA. So you have to put in an extra line. OAN means if I'm going from O down to A in the direction of the arrow, and then back to N, which means I have to go back to N like this, right? So this is my movement. The angle created by that movement is angle OAN, which would be this angle here. That will be the angle OAN. Okay, so that's the angle OAN that is speaking about. What about the angle ONA? Angle ONA is if we're doing the same thing, but going in that direction from O to N to A. So let's go from O to N, which is here, and then from N to A, which is here. And that movement creates another angle here. And that angle is the angle ONA that they're talking about. That angle is the angle ONA, which is this angle here. ONA. Okay? So once you understand what they're asking you to find, then you could go ahead and proceed. The first thing we'll observe is that because of the theorem 6, which says, what does the theorem say for theorem 6? It says that the radius of a circle drawn to the point of contact of a tangent is perpendicular to the tangent. Right? Quite a mouthful. So it means then that OAT must be equal to 90 degrees. OAT must be equal to 90 degrees. So I'm putting in the 90-degree line here. Right? OAT must be equal to 90 degrees because of theorem 6. So you should write that. If you consider, you just write in OAT, that angle that I just identified there, O to A to T, that must be equal to 90 degrees. And the reason for that, I'm just going to write T6, which means theorem 6, right? Because OA is a radius and AT is a tangent. And theorem 6 says that the angle between those two is 90 degrees. So that's why we can say that. Now, how is that helpful to us, or is that helpful to us? Right? One thing we didn't put in this diagram here was the angle up in the corner. Right? Angle up in the corner was important. And that angle was actually 24 degrees. Right? Because the given, in the question it said given that OTA was 24 degrees, which was O to T to A, OTA, it means that the angle here is 24 degrees. So we didn't put that in, you could put it in now. Right? So that angle there is 24 degrees. And if we consider the triangle now, let us consider triangle OAT. If we look at that triangle OAT, then what you will observe is that if we add up all of the angles inside of the triangle, which is angle AOT, let's call that angle AOT for ease of reference. Let's call the angle up here, let's call that angle there alpha, so we could talk about it a little easier. So let me call that alpha there, so you'll be able to follow it. Let's call this angle here alpha. Alright, that's angle alpha. For those of you who can't see that good from far, we're calling that angle inside of there alpha. So therefore, if we consider the triangle OAT, if we add up the three angles, which will be alpha plus the angle down at the bottom here, that'll be 90 degrees, which is angle OAT, and then we add up the one up in the corner, which is angle OTA, that'll be 24 degrees. Then all of that must add up to 180 degrees, right? Because the angles inside of a triangle sum to 180 degrees. So we put in, and we have to put that reason here. Right? The reason why we can say this is because the angles in a triangle sum to or add up to 180 degrees. Okay, so that's the reason we are saying that. And therefore, we could find what angle alpha is by subtracting 180 and minusing 90 and minusing 24. All we did is make alpha the subject of the formula, this angle here, by subtracting 90 and subtracting 24 from the left hand side. Therefore, we have to do it on the right hand side. So it means then that alpha, that angle there, is going to be equal to 180 minus 90 minus 24, which works out to be 66 degrees. So it means that this angle here is equal to 66 degrees. Now, why is that important? Because when we have that angle there, we will be able to find the two angles they're asking us about, which is angle OAN and angle ONA. Okay, so we needed to find the angle at the top here first, which we call angle alpha, and then we are able to find angle OAN and ONA. Okay, so we continue now. If we consider another triangle now, consider triangle. Let's consider another triangle. The triangle we will consider is triangle OAN. That's the triangle we're looking at now. Triangle OAN. If we look at that triangle, what we'll see is that since ON and OA are equal, because they are both radii, right? They are both radii of the circle. OA and ON are both radii, so I'll put R to represent radius. It means that they are equal. So since they are equal, it means then that triangle OAN is isosceles. It's an isosceles triangle. And isosceles triangles are very common, right? You always look out for them because that's what most of the questions are based on, identifying isosceles triangles. Most of these questions, you'll realize that as we go along from this point onwards. And even in the exam, that will be so. So it's an isosceles because those two sides are equal in length. And if that is the case, it means that these two bottom angles, which is OAN and ONA, they must be equal because they'll be base angles of the isosceles triangles. Okay? So triangle OAN is isosceles, and that implies that these two angles, which is OAN, must be equal to ONA. They must be equal to one another since it's an isosceles triangle. The angle alpha up here will be the apex angle, and the other two will be the base angles of the isosceles triangle, and they will be equal. And let's call that, for ease of reference, instead of having to writing that over and over again, let's simply call that theta. So we'll be able to write it easy and not be having to say these long things again. Therefore now, if we know that, we could go back to the same relationship that angles in a triangle sum to 180. So we could add up the three angles now. We could add up angle alpha, which we worked out to be 66 degrees, plus OAN and ONA, which we now call theta. So we're going to add up theta plus theta, and we know that these three must add up to 180 degrees. Right? They must add up to 180 degrees. Let me put in blue what we are calling theta. We are calling angle OAN theta. So here is theta. And we're calling angle ONA theta as well. So there's theta as well. Okay, so that's why I'm saying alpha plus those two angles there must be equal to 180 degrees. So all we have to do is solve this here. So 66 plus 2 theta must be equal to 180 degrees. Right? Which means then that 2 theta must be equal to 180 minus 66 degrees. And therefore, if we divide both sides by 2, we'll get what we want. Which means now that theta, dividing the left-hand side by 2, I'll get theta, must be equal to 180 degrees minus 66 degrees divided by 2. Divide both sides by 2. And once you do that, we'll get the answer of 57 degrees. So seeing that they wanted us to get OAN and ONA and both are equal, which we said was theta, we would have given them their answer right here. The answer is 57 degrees. The answer there is 57 degrees. Okay, so we're looking at theorem 7, which says that tangents to a circle from a common external point T are equal in length. Right? So it means that AT will be equal to BT, simply because they are coming from a common point outside, and we have a tangent, which means it's touching A at this point only, and it's touching the circle, sorry, at A only for that tangent AT, and at B only for the tangent BT. It means that those two lines AT and BT would be equal. Now we have a question that says TA and TB are tangents to a circle center O, and AB is a chord. They want us to calculate AOT and TAB. Now the angle here is given as 56 degrees. Right? That's 56 degrees, first of all. And if we look at the shape OATB, that is a kite. Now the first thing we'll observe is that the angle OAT must be equal to 90 degrees, right? Because of the previous theorem we did, which says that the radii and the radius and the tangent at the point of tangency here intersect at 90 degrees. That was from the theorem we did just before. We also observed that the angle OBT will also be 90 degrees because of that same rule or that same theorem we had studied just before. Right? Because OB is a radius and TB or BT is a tangent. So the angle between them will be 90 degrees. So having observed that, the next thing that we will do is write it here. We write that angle TAO must be equal to angle TBO, and that must be equal to 90 degrees, and that was because of the theorem before, which was theorem 6. Right? So I'll just write T6 here so you'll know what we're talking about. Now the next thing is that because OATB is a kite, and we know that the sum of the interior angles in a kite is 360 degrees, or in any quadrilateral is 360 degrees, we could write that down. We could say that the angle here, which is OAT, which is 90 degrees, plus the angle ATB, which is 56 degrees, plus the angle TBO, which is 90 degrees, plus the unknown angle AOB, right, or BOA is the same thing, which is this angle here. When we add up all those angles, which are the interior angles of the kite, you must get 360 degrees. Right? Because the interior angles of any quadrilateral sum up to 360, and you're supposed to know that. Right? You're also supposed to know the general equation for interior angles is 2n minus 4 times 90 degrees. That's something we studied before, where n is the number of sides. Right? So you could go back and check it, and you could work out the interior angles of any polygon. So from that, we could work out what angle AOB is. Angle AOB would be 360 minus each one of these here. You minus it from this side to get AOB. You have to minus it from the right-hand side as well. So you have to minus 90, minus 56, and minus 90 again. And you'll get what angle AOB is. And that worked out to be 124 degrees. Good? So you know that this whole angle here is 124. However, we don't want this whole angle here. We want the angle AOT. Right now we have AOB, but we want to get AOT. So to get AOT, which will be this part of that angle there will be AOT. AOT. You'll have to know the property that this diagonal OT bisects the angle AOB in any kite, right? It will cut this angle here, AOB, in half. So if AOB we calculated is 124, it means that the angle that they're interested in, AOT, will be half of that. It'll be 124 over 2, and 124 over 2 is 62 degrees. Okay, so we know now that angle AOT is equal to 62 degrees. All right, and the angle, and this is because of the bisection, right? Angle AOB is bisected here. Now, in the handout that you have, I'm going to skip B because B is a more long-winded solution. The solution that goes after, you'll see OR. The first solution, we're not doing that. You see OR, we're going to do that part because that's a more practical solution to do for the second one, which is to find angle TAB. Okay, so we're looking at angle TAB now. And angle TAB requires us to put in another line. Okay, and let's put in that line now because it's not there currently. Let's put in the line TAB. TAB will be this line, we will require this line coming down here. To pick up angle TAB. So TAB will be this angle here. Okay? But interestingly, angle TAB is the same thing as angle TBA, which is this one here. How can I say that? I can say that because of the theorem 7, which says that the tangents to a circle from a common point are equal. So if the tangents are equal in length, it means that the triangle TAB is isosceles. Remember we said isosceles are common, they keep coming back, and you keep looking for it. TAB, that triangle that I'm talking about, that will be isosceles because TA is equal to TB. Right? And if TA is equal to TB, it means that the base angles are these two, right? And those will be equal. So if we make our lives easy and we call this angle here theta, and we call this one here theta as well, then we could solve very easily for what our question is, which is TAB. We are letting TAB equal to theta. TAB, that angle there, we are letting that equal to theta. So if we consider the triangle TAB, since TA is equal to TB, and the reason for that is this theorem, which is theorem 7, I'll just put T7, then TAB, that triangle is isosceles. And if it is isosceles, it means then that angle TAB must be equal to angle TBA because these are base angles. And let us call each one of them theta. Okay? As we did in the diagram. Therefore, what would happen is that if we add up 56 theta and theta, which is 2 theta, we must get the angle, total angle in any triangle, which is 180 degrees. So 56 plus 2 theta is 180 degrees, which means then that we could solve for theta by saying 2 theta would be equal to 180 minus 56. Right? And therefore, if we want to get theta now, all we have to do is divide both sides by 2. Over 2. And if we do that calculation, we'll get 62 degrees. And that's our answer, because we know that TAB is equal to theta, and we just solved theta equal to 62 degrees. Okay? So that was the solution for that particular problem. You're looking at theorem 8. And theorem 8 says that the angle between a tangent to a circle says that the angle between a tangent to a circle and a chord at the point of contact is equal to the angle in the alternate segment. So if this is T, and this is B, this is A, then the angle between the tangent TB and the chord AB is equal to the angle in the alternate segment created by that same chord. So if you look at the chord AB, then if we go to the circumference and come back, we create another angle in here, which will be equal to the angle between the tangent and the chord. So read it back: the angle between a tangent to a circle, TB in this case, and the chord at the point of contact, which is this angle here, is equal to the angle in the alternate segment of the circle created by the same chord. So this is the alternate segment on this side, and this angle is created by the same chord A going down to B. So that angle will be equal. So the question that we face now this angle up here is 35 degrees. This angle down here is 65 degrees. Okay? This is T, B, A, this is E, and this is D. And what they're asking us here is to show, they're saying ATB is a tangent to a circle and CT is a chord. So this is CT here, that's a chord. If TDC is 35 degrees, so TDC 35 degrees are shown, and TCE 65 degrees, TCE 65 degrees are shown, estimate TEC, CTB, and ETA. Okay, so let's look at that here. If we want to get TEC, right, where's TEC? T to E to C is this angle here, and we have to go back as far as theorem 3 to answer that, which says that angles in the same segment are equal, right? Or angles standing on the same chord are equal. So it means that if you look at TC, either that chord or the arc TC, then if we go to one point on the circumference, which is D, and come back, then that will be equal once we go from T to any other point on the circumference and come back to C. So it means that this angle here is also 35 degrees, okay, from theorem 3. So TC is equal to 35 degrees, and that actually is from theorem 3, which we had done before. So now you'll find that you would need to know all of the theorems to be able to solve different questions. The next part was to find angle CTB. Where's angle CTB? Angle CTB is this angle outside here. Okay? That angle outside there. And for that, you have to remember that the angle between a chord, between a tangent and a chord, is equal to the angle in the alternate segment, which is what we just studied here. The angle between the chord and the tangent is equal to the angle in the alternate segment. So if we look at this angle here, and we look at the chord TC, then if we look in the alternate segment, either at this point or at that point E, then you'd realize that the angle down here must also be 35 degrees as well, because of theorem 8, which we just studied. So this must also be equal to 35 degrees. That's because of theorem 8. And the last one, which is answer for C, you're saying they want us to find angle ETA. So let's look at ETA. Where's ETA? ETA. ETA would be this angle here. And this angle is an angle that is also outside, but between the tangent and the chord ET. That's so? It's an angle between the tangent, BTA, and ET. So this angle on the outside will be equal by theorem 8 to the angle created by that same chord on the alternate segment, which will be the angle at this position, which is 65 degrees. So angle ETA is equal to 65 degrees, and that is also from theorem 8, right? Which says that the angle between the tangent and to a circle and a chord at the point of contact is equal to the angle in the alternate segment. Okay, so that would be theorem 8. Yeah. Okay, we're looking at theorem 9. It says that if Tx is a tangent to a circle, as shown, and AB is a secant means a chord that is extended outside, meeting the tangent at x, so the tangent is meeting the secant at this point x, then Tx squared, write it down, Tx squared is equal to AX times XB. Now in the question, they said AB is equal to 9. So what they did in the question is instead, they had the same relationship, but just that Tx was at the bottom. So in the question, they said that AB was 9 centimeters and BX was 5 centimeters. That's what they gave to you. So determine the length of the tangent Tx. So to get Tx, we'd have to know what AX is first. Now AX will be 9 and 5 added together. So AX will be 9 plus 5 to get AX. And you'd have to multiply that by XB. XB is 5. So you put that in there. Okay? So therefore Tx squared will be equal to 9 and 5, 14 multiplied by 5. Therefore Tx will be the square root of 14 multiplied by 5. You have to find square root on both sides. So that works out to be the square root of 70, which works out to be 8.37 centimeters if you round it off to 3 significant figures or to 2 decimal places. Okay? So that is actually the 9 theorems. I don't know if in all schools they teach you all 9. Some schools might teach you 5 and leave you to figure out the rest for yourself, but you need to know all 9 for the exam. Okay? The homework that would be associated with this is certificate maths, exercises 150 and 151. Okay? See how many questions you can do there, and then we'll take it from that position. Thanks for your attention. I know this class was a little long in that sense.